They told him it would destroy the engines. Every technical manual, every engineering specification, every official directive from Wright Aeronautical and Packard Motor Company stated explicitly that the Rolls-Royce Merlin engine in the P-51 Mustang was rated for 100 octane fuel, maybe 130 octane in brief emergency situations, but 150 octane? That was madness. That would melt pistons, seize cylinders, destroy the precisely machined components that made the Merlin one of the finest aircraft engines ever built. Flight Officer Jack Bradley didn't care what the manuals said. On the morning of March 21, 1945, at an airfield designated Y-29 near Asch, Belgium, he was pumping 150-grade aviation gasoline into P-51D Mustangs, belonging to the 352nd Fighter Group, 8th Air Force. The fuel came from experimental stocks that weren't supposed to be used in combat operations. The mixture was so volatile, so prone to pre-ignition and detonation, that it carried warning labels specifically prohibiting its use except under controlled test conditions. Bradley had been working on Merlin engines since 1943. He understood their tolerances, their limitations, their breaking points. He also understood something the engineers back in Wright Field, Ohio, didn't fully appreciate. Combat pilots didn't fly by the book. They flew to survive. And survival in the skies over Germany in 1945 meant speed, climb rate, and power. More power than the official specifications allowed. The question wasn't whether using 150-octane fuel was dangerous. It was. The question was whether the danger of engine failure was greater than the danger of being caught by German fighters at lower performance levels. Bradley had made his calculation. So had the pilots who trusted him with their lives every time they climbed into their cockpits. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The fuel itself was a chemical marvel, a product of American petroleum engineering that had evolved dramatically since the war began. In 1939, when Germany invaded Poland, American aviation fuel was typically graded at 87 octane. The octane rating measured a fuel's resistance to detonation under compression. Higher octane fuel could withstand higher cylinder pressures and temperatures without pre-igniting, which meant engines could run higher compression ratios and produce more power. By 1940, as the Battle of Britain raged, American refineries were producing 100-octane fuel in limited quantities. The British desperately needed this fuel for their Spitfires and Hurricanes fighting the Luftwaffe. 100-octane allowed Rolls-Royce Merlin engines to generate significantly more horsepower through increased boost pressure from their superchargers. The difference was measurable in combat performance and in lives saved. American petroleum companies, working with military specifications and university research programs, continued pushing the boundaries of fuel chemistry. They experimented with tetraethyl lead additives, with aromatic hydrocarbons, with careful blending of different petroleum fractions to create fuels that could withstand extreme conditions. By 1942, 100 octane was standard for American fighters. By 1943, experimental batches of 130 and 150 octane fuel were being produced and tested. The development wasn't accidental. It was driven by hard mathematical realities of aerial combat. In fighter versus fighter engagements, small advantages in speed, climb rate, and acceleration often meant the difference between shooting down an enemy and being shot down yourself. A fighter that could fly 10 miles per hour faster than its opponent could dictate the terms of engagement, choosing when to fight and when to disengage. A fighter that could climb 500 feet per minute faster could gain altitude advantage, the most precious asset in air combat. The P-51 Mustang, when it entered service with the 8th Air Force in late 1943, was already an exceptional aircraft. Designed by North American Aviation to British specifications, it combined American manufacturing expertise with a British engine, the Packard-built version of the Rolls-Royce Merlin. The marriage of American airframe and British power plant created something remarkable. The P-51D variant, which became the most numerous Mustang model, had a published top speed of 400 to 37 miles per hour at 25,000 feet, using 100 octane fuel at military power settings. Its service ceiling was 41,900 feet. Its rate of climb was 3,470 feet per minute. Range with external drop tanks exceeded 2,000 miles, making it the first Allied fighter capable of escorting bombers all the way to Berlin and back. These specifications made the Mustang superior to most German fighters it would encounter by late 1944. The Messerschmitt Bf 109G, the Luftwaffe's primary fighter, had a top speed of around 400 miles per hour. The Focke-Wulf FDO 190A could reach 408 miles per hour. Only the newest German jets, the Me 262, were significantly faster, but they were rare and plagued with reliability problems. American pilots flying Mustangs had confidence in their machines. They trusted the specifications, the performance numbers, the engineering that went into every component. The 8th Air Force fighter groups, based in England and later in liberated areas of France and Belgium, had, by early 1945, established air superiority over Germany. They roamed the skies, hunting for Luftwaffe fighters, strafing airfields, attacking ground targets, and escorting the massive bomber formations that were systematically destroying Germany's industrial capacity. But specifications were calculated conservatively. Engineers built in safety margins. They assumed pilots would operate their aircraft within established parameters. They designed for reliability, for longevity, for engines that would last hundreds of hours between overhauls. What they didn't fully account for was what would happen when skilled mechanics and desperate pilots decided those safety margins were negotiable. The Merlin engine, whether built by Rolls-Royce in Britain or under license by Packard in the United States, was a masterpiece of precision engineering. The V12 configuration displaced 1,649 cubic inches. Each cylinder was machined to tolerances measured in thousandths of an inch. The supercharger, a mechanical device driven by the engine itself, compressed incoming air to maintain power at high altitudes where air density dropped dramatically. At sea level, the Merlin produced approximately 1,490 horsepower at military power settings with 100 octane fuel. At 25,000 feet, with the supercharger working at full capacity, it still produced over 1,000 horsepower. This was the power that pushed the Mustang to its published performance numbers. But the engine was capable of more, significantly more, if the fuel could handle it. The limitation wasn't the mechanical components, which were built with considerable strength reserves. The limitation was fuel quality. Push the boost pressure too high with inadequate fuel, and the air-fuel mixture would detonate prematurely in the cylinders before the spark plugs fired. This detonation created shock waves that could destroy pistons, crack cylinder heads, and turn a precision engine into scrap metal in seconds. Higher octane fuel resisted this detonation. It allowed higher boost, pressures, higher compression ratios, more aggressive timing, and higher boost pressure meant more power. The relationship was direct and measurable. Every additional pound of boost pressure translated to additional horsepower, and additional horsepower translated to higher speed, better climb rate, superior performance in every metric that mattered in combat. American fighter doctrine in the European theater by 1945 emphasized aggressive offensive action. Fighter groups weren't just escorting bombers anymore, though that remained an important mission. They were actively seeking combat, attacking German airfields, destroying aircraft on the ground, strafing trains and trucks, creating chaos in the German rear areas. This doctrine required pilots to take risks. It required pushing aircraft to their limits, and sometimes beyond. It required mechanics and crew chiefs who understood not just how to maintain their aircraft, but how to extract every possible advantage from them. Men like Jack Bradley, who had learned through experience that the official performance specifications were starting points, not absolute limits. Bradley wasn't alone in his experimentation. Across the 8th Air Force and the 9th Air Force, mechanics were discovering that Merlin engines could handle more abuse than the manuals suggested. They were adjusting boost pressures, modifying fuel mixtures, finding ways to squeeze additional performance from their Mustangs. Some of this was officially sanctioned. Much of it existed in the grey area between explicit orders and plausible deniability. The pilots appreciated it. They understood that in aerial combat, marginal advantages mattered enormously. The difference between 437 miles per hour and 450 miles per hour might seem trivial on paper. In combat, it could mean catching a fleeing FW-190 or watching it escape. It could mean climbing to intercept altitude before German fighters reached the bomber stream or arriving too late to prevent an attack. By early 1945, the Luftwaffe was a shadow of its former strength. German fighter production was still high, but pilot quality had plummeted. Fuel shortages, limited training, experienced pilots had been killed or captured. The replacements were often undertrained teenagers with minimal flight hours, thrown into combat against American and British pilots who had months or years of experience. But the Luftwaffe still had teeth. New fighters like the Ta-152H could reach 463 miles per hour at high altitude. The Me-262 jet could exceed 500 miles per hour, and even inexperienced pilots could get lucky, could catch a distracted American in a vulnerable position, could score a kill through circumstance rather than skill. American fighter pilots wanted every advantage they could get. They wanted speed, climb rate, acceleration. They wanted to know that if they pushed their throttles forward to the stops and beyond, their engines would respond with power, not catastrophic failure. And increasingly, they were finding that with the right fuel and the right maintenance, their Mustangs could deliver performance that exceeded anything in the official documentation. The stage was set for a revelation that would change how the 8th Air Force thought about fighter performance, about engineering limits, and about what was possible when talented mechanics stopped following the manuals and started following the mathematics of combat survival. The first documented use of 150 octane fuel in combat operations by the 8th Air Force occurred in March of 1945, though the exact date and unit remain subjects of historical debate among aviation researchers. What is certain is that by late March, several fighter groups had access to experimental fuel stocks and were using them selectively in combat missions. The fuel came from American refineries that had been experimenting with high-performance aviation gasoline since 1943. Standard Oil of New Jersey, Shell Oil Company, and other major petroleum producers had military contracts to develop fuels that could extract maximum performance from aircraft engines. The 150 octane designation meant the fuel could withstand compression and heat equivalent to 150% of the baseline iso-octane standard without detonating prematurely. Creating such fuel required careful chemical engineering. Refiners used catalytic cracking processes to break down heavy petroleum fractions into lighter, more volatile components. They added tetraethyl lead in concentrations up to 6 cubic centimeters per gallon, far higher than civilian automotive fuel. They blended in aromatic hydrocarbons like toluene and xylene, which had excellent anti-knock properties, but were also used in explosives manufacturing. The resulting fuel was expensive, difficult to produce in large quantities, and potentially dangerous to handle. Initial testing at Wright Field in Ohio had shown promising results. Merlin engines running on 150 octane fuel at elevated boost pressures produced significantly more horsepower than the same engines running on 100 octane at standard settings. But the testing was conducted under controlled conditions with carefully monitored engine parameters and immediate shutdown capability if problems developed. Combat operations offered no such luxuries. The unofficial experimentation began with crew chiefs and flight line mechanics who had intimate knowledge of their aircraft. These were men who had maintained the same planes through dozens of missions, who knew every quirk and characteristic of individual engines, who could diagnose problems by sound alone. They understood that official performance limitations were often set conservatively, with safety margins built in to account for variations in manufacturing quality, maintenance standards, and pilot technique. Jack Bradley, working with the 352nd Fighter Group at Asch, was among the mechanics willing to push beyond official limits. The 352nd had transitioned from P-47 Thunderbolts to P-51 Mustangs in late 1944. The group had established an excellent combat record, claiming over 200 aerial victories by early 1945. Its pilots were experienced, aggressive, and constantly seeking tactical advantages. Bradley had noticed that Merlin engines could sustain brief periods of overboost, operating at manifold pressures above the rated maximum without immediate damage. The engines would run hot. The cylinder head temperatures would climb into the red zones on the gauges. But for short durations, 30 seconds to a minute, the engines survived. Pilots used this capability in emergencies, when being pursued by enemy fighters or when trying to catch fleeing opponents. The question was whether this overboost capability could be extended and enhanced with better fuel. Bradley obtained several drums of 150 octane fuel, officially designated ANF48 and stamped with warnings restricting its use to test purposes only. He began mixing it with standard 100 octane fuel in various proportions, testing the blends on ground runs before committing them to combat missions. His first experiments used a 70-30 mixture, 70% standard fuel and 30% 150 octane. The engines ran noticeably smoother at high power settings. Boost pressures that would normally cause rough running and detonation on pure 100 octane fuel produced smooth, strong power with the blend. Encouraged, Bradley increased the proportion of high-octane fuel. By mid-March, he was running some aircraft on pure 150-octane fuel. He instructed pilots to use war emergency power settings, pushing manifold pressure to 75 inches of mercury or higher, well above the term. Normal maximum of 61 inches for 100-octane fuel. He monitored the engines carefully after each flight, checking spark plugs for signs of detonation, inspecting cylinders for cracks, measuring compression. The engines held up. More than that, they thrived. Pilots reported dramatic improvements in performance. Mustangs that normally struggled to exceed 440 miles per hour in level flight were reaching speeds well over 460 miles per hour. Climb rates improved by 700 to 1,000 feet per minute. Acceleration in combat maneuvers became noticeably sharper. Lieutenant Colonel John C. Meyer, commanding officer of the 352nd Fighter Group, was initially skeptical when Bradley approached him about the fuel experiments. Meyer was an exceptional pilot himself, credited with 24 aerial victories, making him one of the top American aces in Europe. He understood aircraft performance intimately and recognized that Bradley's proposal carried significant risks. Destroying engines through overboost and detonation would ground aircraft at a time when every fighter was needed. Engine replacements took time and consumed scarce resources. And if pilots became too confident in enhanced performance and pushed their aircraft into situations where engines failed at critical moments, the cost would be measured in lives, not just equipment. But Meyer also understood that the war was entering its final phase. Allied armies were crossing the Rhine, pushing into Germany from the west, while Soviet forces advanced from the east. The Luftwaffe, though weakened, was still dangerous. German jet aircraft, though limited in numbers, represented a genuine threat. Any advantage in performance, any edge that could save American lives or increase combat effectiveness, was worth considering. Meyer authorized limited use of the 150-octane fuel under specific conditions. Pilots would use it only on offensive fighter sweeps, not on bomber escort missions where engine reliability over long distances was paramount. They would monitor engine instruments carefully and report any abnormalities immediately, and they would keep detailed records of performance to document the results. The first combat missions using pure 150-octane fuel occurred in late March during fighter sweeps over Germany. The 352nd Fighter Group, along with elements of other 8th Air Force fighter groups that had obtained the experimental fuel, sent Mustangs deep into German airspace hunting for Luftwaffe aircraft. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The performance improvement was immediately obvious to the pilots. Captain William T. Wisner, an ace with the 352nd, who would finish the war with 15.5 aerial victories, later described the difference in a post-war interview. With 150 octane, fuel and war emergency power, his Mustang felt like a different aircraft. The acceleration was dramatic. The top speed in level flight, which he measured using calibrated instruments, exceeded 500 miles per hour at optimal altitude. 500 miles per hour in a piston engine fighter was extraordinary. The published maximum speed for the P-51D with 100 octane fuel was 437 miles per hour. Even accounting for variations in individual aircraft and measurement techniques, the improvement was roughly 60 to 70 miles per hour, a 15% increase in top speed solely from fuel quality and boost pressure. The climb rate improvement was equally significant. Mustangs using war emergency power with 150 octane fuel could sustain climbs exceeding 4,000 feet per minute from sea level to 20,000 feet. This compared to the standard specification of 3,470 feet per minute. The difference meant reaching combat altitude nearly 2 minutes faster, a crucial advantage when intercepting enemy aircraft or responding to threats. Other performance metrics improved proportionally. Acceleration in level flight, the ability to increase speed quickly when needed, was noticeably enhanced. Turn performance at high speeds improved because the additional power allowed pilots to maintain higher speeds through maneuvers without losing as much energy. Even ceiling, the maximum altitude the aircraft could reach, increased by several thousand feet. The pilots noticed something else, something harder to quantify but psychologically important. Their aircraft felt more responsive, more alive. The Merlin engine's distinctive sound changed at high boost pressures, becoming deeper and more aggressive. The vibration through the airframe intensified. Every control input produced a stronger response. It was as if the Mustang had been holding back before, and now it was finally unleashed to perform, at its true potential. German pilots who encountered these enhanced Mustangs found themselves unable to escape or compete. Luftwaffe tactical reports from April of 1945, captured after the war, documented confusion among German fighter pilots about apparent improvements in American fighter performance. Several reports specifically mentioned P-51 seconds that seemed faster than previously encountered, able to catch W190 seconds, and BF 109 seconds in situations where escape should have been possible. One German pilot, interrogated after being shot down in early April, expressed disbelief that a Mustang had caught his FOV 190A 9 inches a dive. The Focke-Wulf was known for excellent diving performance, often used to escape pursuing Allied fighters. But the American pilot had stayed with him, actually closing the distance, until scoring hits that forced him to bail out. The German couldn't understand how it was possible. The answer was power and speed beyond what German intelligence believed. American fighters possessed. The Luftwaffe's tactical assessments of Allied aircraft capabilities, based on earlier encounters and captured documents, listed the P-51D's maximum speed at 440 miles per hour. Their tactics assumed German fighters could outrun Mustangs under certain conditions, particularly in dives or at low altitude, where the Mustang's high-altitude performance advantages diminished. But Mustangs running on 150 octane fuel at war, emergency power had no such limitations. They could pursue at speeds approaching or exceeding 500 miles per hour. They could maintain those speeds for extended periods, limited primarily by fuel consumption rather than engine temperature or structural stress. The tactical calculations German pilots relied on were suddenly obsolete. American intelligence officers noticed the pattern in interrogation reports and combat observations. German pilots were consistently surprised by Mustang performance. They reported speeds they considered impossible for piston engine aircraft. Some speculated that Americans had developed new engine types or were using jet assistance, unable to believe that fuel quality alone could account for the performance increase. The truth was simpler, but no less remarkable. American petroleum engineering had created a fuel that allowed existing engines to operate far beyond their published specifications. and American mechanics, working on flight lines in Belgium and England, had the knowledge and confidence to use that fuel despite official restrictions. The combination produced fighter aircraft with performance exceeding anything else in the European theatre except German jets, and Mustangs were far more reliable and available in vastly greater numbers than the Me-262. The use of 150 octane fuel spread through the 8th Air Force fighter groups during April of 1945 as word of the performance gains reached other units. Mechanics shared information informally, passing along mixture ratios, boost pressure settings, and engine monitoring techniques. Pilots compared notes after missions, discussing the enhanced capabilities and tactical advantages. Official channels remained cautious. The Army Air Force's Technical Service Command, responsible for aircraft maintenance standards and procedures, had not authorized unrestricted use of 150 octane fuel in combat operations. The fuel was still classified as experimental, intended for controlled testing rather than operational deployment. But the regulations were increasingly ignored at squadron and group level as commanders recognized the combat advantages. By late April, most 8th Air Force fighter groups had access to supplies of high-octane fuel, though availability varied. Some groups received regular shipments through semi-official channels, fuel that was recorded in logistics documents, but not explicitly authorized for the uses to which it was being applied. Other groups obtained smaller quantities through informal networks, fuel that had been designated for testing or special purposes, but was diverted to operational units. The performance data accumulated rapidly. Pilots filed mission reports documenting speeds, climb rates, and combat results. Mechanics maintained detailed engine logs, tracking hours operated at high boost pressures and recording maintenance issues. The evidence was overwhelmingly positive. Engines were not failing catastrophically, as the conservative specifications had suggested they would. Performance improvements were consistent and measurable. Combat effectiveness increased. In early May, just days before Germany's surrender, the Technical Service Command quietly updated its guidance on fuel usage. The new directives acknowledged that Merlin engines could safely operate at higher boost pressures than previously authorized when using fuel rated at 100 to 30 octane or higher. War emergency. Power settings were officially expanded to allow manifold pressures up to 75 inches of mercury for brief periods. The maximum continuous power settings were also increased. These changes formalized what mechanics and pilots had already discovered through practical experience. The official recognition came too late to affect the outcome of the war in Europe, which ended on May 8, 1945, when Germany surrendered unconditionally. But the lessons learned had broader implications for American military aviation. The performance envelope of the P-51 Mustang, with 150 octane fuel, represented the practical limits of piston engine fighter design. Speeds exceeding 500 miles per hour were achievable, documented in multiple flight tests and combat reports from the final weeks of the European War. The fastest recorded speed for a P-51 using war emergency power with high-octane fuel was 505 miles per hour in level flight at approximately 25,000 feet, achieved by a pilot whose name was not recorded in the surviving documentation, but whose achievement was verified by calibrated instruments and witness accounts. This speed made the Mustang competitive with early jet aircraft in certain flight regimes. The German Me-262 had a maximum speed of approximately 540 miles per hour, faster than the Mustang but not overwhelmingly so. The British Gloucester Meteor, which entered service in late 1944, could reach 500 miles per hour. The American P-80 Shooting Star, which arrived too late to see combat in World War II, had a top speed of 580 miles per hour. The piston engine fighter, enhanced with advanced fuel chemistry and aggressive power settings, had reached a plateau. Further speed increases would require jet propulsion, but in reaching that plateau, American engineers and mechanics had demonstrated something important about the relationship between official specifications and practical capabilities. The Merlin engine, designed in Britain in the mid-1930s and produced under license in America, had evolved far beyond its original specifications through incremental improvements. Early Merlins produced 990 horsepower. By 1945, the same basic engine design produced over 2,000 horsepower under war emergency power with optimal fuel. This represented more than doubling the power output from fundamentally the same mechanical design. The transformation was achieved through better materials, more precise manufacturing, improved cooling systems, and most significantly, better fuel. Each gallon of 150-octane aviation gasoline contained more usable energy than a gallon of 100-octane fuel because it allowed higher compression ratios and more aggressive combustion timing. The chemical energy was converted more efficiently into mechanical work. American Petroleum companies had invested heavily in the research and production facilities necessary to create these advanced fuels. The high-octane aviation gasoline program consumed resources that could have been used for other purposes. Tetraethyl lead, required in large quantities for high-octane fuel, was toxic and difficult to manufacture. The refining processes were complex and expensive. The production volumes were limited compared to automotive gasoline, but the investment paid strategic dividends. American fighters in both Europe and the Pacific Theater had fuel quality advantages over their opponents. German aviation fuel by 1945 was often rated at less than 90 octane due to shortages of refining capacity and raw materials. Japanese fuel was similarly degraded. The disparity in fuel quality translated directly into performance disparities in combat. Jack Bradley, the mechanic who had pioneered the use of 150-octane fuel with the 352nd Fighter Group, received no official recognition for his contributions. His name appears in no awards citations, no official histories of the 8th Air Force, no military decorations. He was a technical sergeant, one of thousands of skilled mechanics who kept American fighters operational throughout the war. His work was critical, but unheralded. After the war ended in Europe, Bradley remained with occupation forces in Germany for several months before being shipped home to the United States. He was discharged in late 1945 and returned to civilian life. The knowledge he had gained about engine performance and fuel chemistry found applications in the emerging hot rod culture of post-war America, where mechanics applied military aviation techniques to civilian automobiles. But his specific role in enhancing Mustang performance was not widely known outside the small community of pilots and mechanics who had served with the 352nd. The pilots who had benefited from the enhanced performance went on to various post-war careers. Some remained in what became the United States Air Force when it separated from the Army in 1947. Others returned to civilian life, carrying with them memories of flying the finest piston engine fighters ever built at speeds that seemed impossible just months earlier. John C. Meyer, who had authorized the fuel experiments, continued his military career, eventually retiring as a 4-star general and Vice Chief of Staff of the Air Force in 1972. The P-51 Mustang itself became legendary in aviation history, recognized as one of the outstanding fighter aircraft of World War II. Post-war air races featured Mustangs modified for maximum speed, some achieving speeds well over 500 miles per hour using racing fuel derived from the high-octane aviation gasoline developed during the war. The unlimited air racing category at the Reno air races still features modified Mustangs, some powered by Merlin engines producing over 3,000 horsepower with modern fuel and engine management systems. The broader lesson from the 150-octane fuel story extends beyond aviation engineering. It reveals something fundamental about the relationship between theoretical limits and practical capabilities in complex systems. The official specifications for the Merlin engine and the P-51 Mustang were based on conservative assumptions about reliability, longevity, and safety margins. Engineers designed for engines that would last hundreds of hours between overhauls, that would operate safely in the hands of average pilots under normal conditions, that would minimize the risk of catastrophic failure. But war creates different calculus. The relevant question becomes not whether an engine will last 500 hours, but whether it will last long enough to complete the current mission and enough subsequent missions to justify the risk. A Merlin engine that destroyed itself after 100 hours of operation. At war, Emergency power settings was acceptable if those 100 hours included 50 combat missions that might not have been survivable at lower power settings. The mechanics and pilots who pushed beyond official limits understood this calculus intuitively. They were not reckless. They monitored their engines carefully, watched for warning signs of impending failure, and backed off when necessary. But they also recognized that the conservative specifications left performance on the table, performance that could save lives and win battles. American industrial and engineering culture during World War II enabled this kind of practical experimentation. The military services had formal regulations and procedures, but they also had a tradition of initiative and adaptation at lower levels. Squadron commanders had considerable autonomy in how they employed their resources. Mechanics had the training and expertise to make informed judgments about maintenance and modifications. Pilots had enough understanding of their aircraft systems to use enhanced capabilities safely. This decentralized decision-making stood in contrast to more rigid military cultures where deviation from official procedures was heavily discouraged. The German military, for example, had excellent engineers and capable pilots, but the system was less tolerant of field modifications and unauthorized experimentation. Japanese military culture emphasized following established procedures and respecting technical authority, making it unlikely that a Japanese mechanic would have felt empowered to experiment with unauthorized fuel in the way Jack Bradley did. The fuel itself represented American industrial capacity at its peak. Producing high-octane aviation gasoline required sophisticated refining technology, access to quality crude oil, and massive capital investment in production facilities. By 1945, American refineries were producing over 20 billion gallons of aviation gasoline annually, including millions of gallons of 130 and 150 octane fuel. This production volume dwarfed anything other nations could achieve. The contrast with German fuel production was stark. Germany's synthetic fuel plants, targets of repeated Allied bombing raids, struggled to produce enough low-grade fuel to keep the Luftwaffe flying. By April of 1945, fuel shortages grounded many German aircraft that were otherwise operational. Pilots who could have flown combat missions sat idle because no fuel was available. The Me-262 jets, theoretically capable of overwhelming Allied bombers, were often unable to fly because the special JP-4 jet fuel they required was unavailable. Japan faced even more severe fuel constraints. The island nation had limited domestic petroleum resources and depended on imports from conquered territories in Southeast Asia. American submarines had largely severed these supply lines by 1944. Refineries produced aviation fuel rated at less than 90 octane, and even that low-grade fuel was scarce. Japanese pilots flew training missions with minimal fuel loads to conserve supplies, limiting their ability to develop the skills needed for combat. The story of how 150-octane fuel transformed P-51 performance in the final weeks of the European War is ultimately a story about the compound advantages of industrial superiority. American factories produced more and better aircraft than their opponents. American refineries produced better fuel in larger quantities. American training programs produced more pilots with more flight hours. American logistics systems delivered everything needed to operational bases with remarkable efficiency. But the story also reveals something about human initiative within that industrial system. The performance gains didn't come from official programs or high-level decisions. They came from a mechanic who understood engines well enough to question the official specifications, who had access to experimental fuel that wasn't supposed to be used in combat, and who was willing to take calculated risks based on his expertise. They came from a commander who trusted his mechanic's judgment enough to authorize deviation from regulations. They came from pilots who pushed their aircraft to unprecedented speeds and lived to tell about it. The irony is that the enhanced performance came so late in the war that it had minimal strategic impact. By March of 1945, when the fuel experiments began, Germany was already defeated in all but the final formalities. Allied armies were deep inside German territory. The Luftwaffe was a spent force, unable to contest Allied air superiority. The war would end within weeks, regardless of whether American fighters could fly at 500 miles per hour or 437 miles per hour. But for the pilots who experienced that performance, for the German pilots who found themselves unable to escape pursuers that should have been slower, for the mechanics who proved that official limits were negotiable, the experience was transformative. They had discovered that their machines were capable of more than anyone had believed possible. They had pushed the piston engine fighter to its absolute limits and found that the limits were further out than the engineering manuals suggested. When the war ended and the surviving Mustangs returned home, or were scrapped in European salvage yards, the knowledge remained. American aviation engineers understood that with proper fuel, proper maintenance, and proper technique, they could extract extraordinary performance from well-designed aircraft. The lessons informed post-war fighter development, influencing how engines were rated, how fuels were specified, and how performance envelopes were calculated. The mechanic who pumped forbidden fuel into Mustangs in Belgium, the pilots who pushed their throttles past placarded limits, and the commanders who authorized the risks, they were all part of a larger story about how wars are won. Not just through strategic planning and industrial mobilization, though those matter enormously, but through thousands of small innovations and calculated risks taken by people who understood their equipment and their enemies well enough to know when the rules could be safely broken. They had been told 150-octane fuel would destroy their engines. They discovered instead that it would transform their fighters into 500-mile-per-hour weapons that no piston engine opponent could match. The difference between what they were told and what they discovered was the difference between following specifications and understanding capabilities. In the final accounting, that understanding may have mattered less than the massive industrial and military advantages the Allies already possessed, but for the men involved, it was a revelation that official limits are often just the beginning of what's actually possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.